You know what, Lexi? I'm really glad you asked because I haven't been recording this. No, I haven't. I asked you guys, to make sure I'm recording. So, Lexi, you did me a good turn here by asking me to repeat myself. So I'm going to, but I'm going to do it in a condensed form. Remember, I'm an absent-minded professor, okay? That's my job. I mean, mostly to be a professor. And I generally have mastered this technology, but sometimes I get very engaged in the subject matter as a teacher. I enjoy, the subject, and I enjoy teaching it, and I enjoy interacting with you guys. So sometimes I forget to flip that little switch about turning the recording on. So please remind me when I say good morning to you all. Don't be shy, okay? I appreciate you reminding me to turn on the switch. Okay, so Lexi, what I said was, in a nutshell, that we can resolve a paradox, and the price we pay for resolving a paradox is some shift in our thinking, and that a paradox stems from basically going wrong somewhere in what seems a very plausible set of assumptions, which somehow concludes with something crazy or impossible or implausible, and that the way of resolving it is to go back and understand what went wrong in our thinking, and that we can do. But very often, or almost always, there's a price, as I said, an epistemological price, that when we resolve a paradox by discovering what was wrong in our reasoning, we'll also have to make some adjustments to our way of looking at things. And that's the sort of a price that we pay, okay? So the first paradox is that you can't leave the room. And of course you can leave the room, and the reason you can leave the room is that you're only a finite distance from the door, whether it's 5 feet or 10 feet. And you can always take a finite number of steps to cover that distance. The counterintuitive thing is that if we stop to count the number of points on the way, we'll never get there, because there are an infinite number of points, right? Obviously, whether you're 5 feet from the door or 10 feet from the door, the number of points between you and the door is infinite. And so that first paradox appears paradoxical only because Zeno concocted the problem in such a way as to conflate the length of a line or the length of an interval with the number of points it contains. And we know now that one has nothing to do with the other. And that's the strange thing, right? The price we're paying for resolving the paradox is this strange and somewhat counterintuitive notion that, in fact, the number of points on a line is independent of its length, or said a different way, that every line segment, regardless of its length, contains an infinite number of points. And that's a bit bizarre, right? So we're saying that a 5-foot segment contains the same number of points as a 10-foot segment. Isn't that a little strange? Yes, Mame, of course, yes. I think Mimi, all of you, or some of you are saying, yeah, it's extremely strange. So we hadn't considered that before. But obviously we know we can all leave the room. And so that's the point. The way we leave the room is by disregarding the fact that regardless of your foot size, your shoe size, or regardless of the length of your stride, every step you take, whether if you measure it in a finite way, maybe you're taking a step that's a foot long, or a big step, giant step, maybe 3 feet long or whatever, but you're stepping over an infinite number of points. And now, Abraham, because you're very philosophical, Abraham, you're asking a more complicated question. Does infinity exist in the real world, or is it just a mathematical concept? Well, that's a great question, and I'm not so sure you're going to get consensus. If you went to a mathematics department, or if you went to a physics department, you might get very different answers, okay? From a philosopher, all bets are off. Here's what I want to say to you, okay? Suppose you actually take a line, like we saw with that diagram last day, like just take a straight line, and take a ruler and start dividing it, okay? There's no end to the division that you could make, right? You could divide the line in half, and then you could divide the line in quarters, and then you could divide the line in eighths and sixteenths, and it's 1/2 to the end. Could you not? You could keep dividing that line, right? And so why would you think that infinity is just a concept? If there's no end to the divisions of that line, and if you took a microscope and magnified the line, you'd see more ways to divide it. You could divide it with it, and you never get to the end, right? You could keep dividing it and never reach the end of the division. And so why would you then suppose that infinity is just a mathematical concept? what infinity really means is not a number, right? You can't divide a line an infinite number of times. That's a contradiction in terms. The infinity is not a number. Remember, infinity means something that increases without bound. So there's no upper limit. There's no final number that you reach. But you could just keep dividing and never finish. And to me, that's real. Maybe there are a finite number of atoms in the world. And so if we started counting all the atoms in the world, we might reach some finite number of them, to be sure. But on the other hand, if we started counting numbers themselves, if we started making a list of all even numbers or all odd numbers or all counting numbers, we'd never reach the end. And so it seems to me that that's more than a concept. It seems that if we try to translate that concept into some kind of physical representation, it never ends in the real world. Okay? On the other hand, you could say that it just is a concept that we really fail in some way to translate, right? But I leave it to you. That's a really great question, Ibrahim, and I think that whatever answer you want to come up with, maybe I'll put that on a future essay question list, okay? I think it's very interesting indeed. But remember that infinity means increasing without bound. There's no end. So maybe this universe is infinite. We don't even know that, right? Isn't it possible, let me just ask you, since we're being imaginative this morning, isn't it possible that this whole universe, this whole vast universe with its, I guess, billions, if not trillions of galaxies and uncountable numbers of stars and even more atoms than that, I mean, it's just huge, gargantuan, beyond imagination. What if that were just a grain of sand on a beach? Isn't it possible that what we consider to be the whole universe is just a grain of sand on a beach? Sure it is. Yeah, it's possible, right? And so then, in that case, you can't count all the grains of sand on a beach. It's still finite. There are finite grains of sand on a beach. But imagine now that that beach is a world, itself in a bigger universe, right? So every grain of sand on that beach contains a universe, but that beach itself is on a little planet somewhere in an even bigger universe, right? Which is itself a grain of sand on another beach, okay? And suppose that never ends. Yes, then it would truly be infinite, Mame. Exactly, that was my point. So in that case, then infinity would be real, and it wouldn't just be a concept, okay? But nobody really knows. Okay, so that's why it's a philosophical question. But I'm glad you're asking. I'm glad you're asking. So physical reality could itself be as much of an infinite regress as just mathematical conceptualization. Okay, great stuff. I'm glad you're asking these questions this morning. So let's go on now to the Achilles and the tortoise paradox, shall we? And see how that gets resolved. You remember I very briefly posed the problem to you at the end of Monday's plenary. So I want to re-show that slide to you now. We'll share that screen again and reconstitute the problem and see how we can resolve it. Let me just find the share and the window, and here we go. Okay, so this is just one schematic way of representing it. You've got Achilles, who we know is a super fast runner. He's faster than Usain Bolt, okay? Achilles is like totally the fastest runner we could think of. And the tortoise is really slow. You know that tortoises are slow. Tortoises are not turtles. Tortoises are land-based reptiles that look like turtles, cousins of turtles. Has anybody seen a Galapagos tortoise, like a giant tortoise? And the bigger they are, the slower they are, right? And I think they move like super slowly. They see a piece of lettuce and they start sprinting after it, but they're moving maybe at the most a couple of feet an hour or something. They're moving at a ridiculously slow speed. Okay, very slow speed. So that's the tortoise. Okay, so here's how the problem is set up. This is Zeno's paradox of Achilles and the tortoise. He says, suppose they're running a race. And of course, it's got a finite distance. So there is a finish line. There's a starting line at A, and it's going to finish somewhere, an unspecified distance away. Doesn't matter. It's finite. The race itself is finite. So we know they're going to finish the race at some point in time. And we also know that because the tortoise is so slow compared to Achilles, we're going to give the tortoise a head start. And so Zeno's argument is as follows. He says, all right, we'll suppose that Achilles is waiting at the starting line at A, and he's going to wait. We're going to wait until the tortoise reaches a certain point B. Again, it doesn't matter what the actual numbers are. Some head start, and at point B, then the gun will fire and Achilles can start running. Okay? Now, we know that Achilles is going to reach point B a lot faster than the tortoise because Achilles is a lot faster. But even so, by the time Achilles reaches point B, where the tortoise was, we call this now A prime. It's the same point, right? We know that however quickly he got there, the tortoise is going to go a little further ahead because the tortoise had a head start already. And the tortoise started at B when Achilles started at A. So by the time Achilles gets to this point, B or A prime, same point, we know the tortoise is going to be a little further ahead at B prime, less far than the beginning, because Achilles will make up the difference a lot quicker than the tortoise covered it, but he'll be a little further ahead. And so the same argument applies. Now Achilles will even more quickly catch up to B prime. We call that A double prime, same point. But even so, when Achilles reaches that point, the tortoise will still be just a little bit further ahead because the tortoise is always ahead. And similarly, when Achilles, just extrapolate the argument, when Achilles gets to this point, which would be A triple prime, then the tortoise will be at B triple prime, a little further ahead. Notice that the lead that the tortoise has is constantly diminishing, right? Because Achilles is a faster runner, and so he's going to make up those ever diminishing leads with an ever decreasing amount of time. But even so, as soon as he gets to where the tortoise was, the tortoise is always going to be a bit further ahead, and therefore, concludes Zeno, Achilles could never catch the tortoise. That's Zeno's conclusion. So no matter how fast Achilles is, if the tortoise gets any kind of a head start, Achilles is never going to be able to catch the tortoise. And that's paradoxical, clearly, because we know that Achilles is much faster than the tortoise. And we also know, I hope you all know, from your common sense and experience of life, that if the race goes on long enough, then there's no question that Achilles is going to catch and pass the tortoise, and will never be after that point behind, right? At a certain point, we know Achilles will draw a level with the tortoise, and we also know that Achilles will pull ahead of the tortoise, and then Achilles will, after that, always be in the lead, and will increase the lead until he reaches the finish line, correct? Well, that's what our common sense tells us, is it not? Of course it does. We know this. Of course we know this. But then the question is, well, what's wrong with the argument? Because the argument is leading us to a seemingly absurd conclusion, namely that Achilles can't ever catch the tortoise. And yet the argument makes a lot of sense, right? Because, again, I'll repeat the argument. You give the tortoise a head start. So he's at B when Achilles, well, by the time Achilles gets there, the tortoise is a little further ahead, no question. And by the time Achilles gets there, tortoise is a little further ahead again. And by the time Achilles gets there, the tortoise is a little further ahead again. So no matter how many times you iterate that argument, it appears that the tortoise is indeed always a little bit further ahead of Achilles. So our problem then is to articulate what's wrong with that argument. Why is it a little further ahead? Because we gave the tortoise a head start. The simple reason that we gave the tortoise a head start, Mimi. I mean, here, go back to the beginning, okay? We've said that Achilles and the tortoise are lined up at point A, all right? But then we say we're going to give the tortoise a head start. So we're going to say to Achilles, you can't run yet. We're going to let the tortoise start running first, or, waddling, or whatever tortoises do. So, of course, the tortoise, by definition, is ahead because we've created the condition that the tortoise gets to run first and Achilles has to wait. And then we let Achilles run. But then when Achilles starts running, before he can overtake the tortoise, he has to get to the point where the tortoise was. But then by that time, the tortoise is a little further ahead. Okay? Is that clear? Are you okay with that, Mimi?
Can I ask a question?
Please.
So just to clarify my thoughts, in case I'm wrong, I'm reading like the chart, right? And it says from distance A to B is like 10 meters or something, and then the second one is like 1 meter, and then the third one is like 0.1 meter or something.
Yeah.
If it's like what you said, does it kind of like the tortoise always ahead because of infinity when you go down to 0.01 meters or
That's right.
0.001?
That's right. In other words, we assume, I'll just make this to be very clear, the numbers don't matter. They're just in there to give you an illustration that Achilles is constantly closing the gap. But the point is that they're both running with a constant speed, okay? That's very important to the physics, because actually those of you who do Physics 101 would know that if we knew the actual speeds, whatever they might be in miles per hour or meters per second, doesn't matter. And if we knew the actual head start that the tortoise was given, we would be able to calculate with very simple formulae. We'd be able to predict exactly when Achilles overtakes the tortoise, right? We would know the exact moment in time and in space where they would draw a level, and we would also know after that Achilles pulls ahead. But this first part of the argument is correct because before Achilles catches the tortoise, we know that he's behind by, in this problem, they're saying we're giving the tortoise a 10-meter head start, and we're assuming that Achilles runs maybe 10 times faster than the tortoise. So by the time Achilles closes that distance, the tortoise is, 1 meter ahead. And then Achilles closes that distance even more quickly because it's shorter. But by the time Achilles runs that 1 meter, the tortoise is 0.1 meters ahead. And we can extrapolate that, right? By the time Achilles closes that 0.1 meter gap, the tortoise is 0.01 meters ahead. And then it'll be 0.001 meters ahead. So Achilles is always closing the gap, and without a doubt. But on this view, on Zeno's argument, although Achilles is always closing the gap, every time he gets to where the tortoise is always going to be a little bit further ahead. So he can never catch the tortoise. Now we know that can't be true, but our challenge is to pick out what's wrong with the argument. All right? Is that much clearer, Mimi? Yes? Yeah, it's a great story. Zeno was really good at challenging us because he's telling us something which is ridiculous, but we're not able to penetrate very easily or very immediately what's going wrong in his argument. That's why it's a paradox. Okay, that's what a paradox does. It challenges our thoughts. A paradox is a great thing because it forces us to see more clearly into something that we were not really clear about to begin with. And once I tell you what's wrong, and I can do it in one sentence of English, and I will, and it will make a light come on. Some of you will not understand it right away, but when you do understand, you're going to say, here we go. Okay, meanwhile, Mame asked, doesn't Achilles have a weakness? Yeah, he has an Achilles heel. That's where the expression comes from, right? Achilles is like a god or almost a god, right? He has an Achilles heel, and that is his heel is vulnerable. I think that's how they kill him, with an arrow in the heel, right? But that's a different story. Right? That's a different part of Greek mythology. This isn't part of Greek mythology. This is just he's using Achilles as, an example of a supremely fast sprinter. Okay? Are we all right so far? So far so good. You understand the problem, right? Good. Okay. So I don't want to keep you in suspense too long. And Mimi saying, I'm wondering, may the tortoise and the hare story. Well, again, look, I wouldn't now take this, as a door to open onto Aesop's fables or, Grimm's fairy tales or anything. There are all kinds of fables involving animals. So I'm not saying there's a relation. I'm just saying this is a much older problem, and they happen to be using a tortoise, okay? Because we know tortoises are slow. Okay. So does anybody have any idea? Does anybody want to guess? Or does anybody have any thoughts at this point? I'm going to tell you in a minute what I mean. I'm not dictating to you, but there is a very clear solution, it seems to me. At least I'm convinced by it, and most others. Philosophers love to disagree with each other, But the solution I'm going to reveal to you in a moment is one that I think even philosophers agree on. So it's pretty clear. It's pretty incontrovertible. But it's also going to, again, enforce that condition I told you about. It's going to make us look at things in a slightly different way. Okay, and it's also related to the first one. So, do you want me to just tell you, or do you want to? Anybody want to take a wild guess? Okay, Elijah. If Achilles is moving at a faster rate, he eventually won't be. Yes, that's absolutely right. But why don't we ever find that point according to this argument? You see, Elijah's saying if Achilles is moving at a faster rate, which he is, eventually he won't be closing the gap. He will have surpassed the point the tortoise has gotten to. Absolutely correct. But what Zeno is saying is the following, and please let's nuance the argument a little more. Before he surpasses the tortoise, he has to catch the tortoise, right? There's no way he can pass the tortoise without at some time drawing level with the tortoise, correct, Elijah? Yes. I mean, it's absolutely irrefutable that if you're going to pass somebody in a race, there's some point at which you draw even with them and then you go ahead. You can't, it's impossible for you to pass somebody without ever drawing even with them first. I mean, that's clear, okay? But this is where we have to focus. This is the point at which you have to focus, because what Zeno is telling us, Zeno is not denying what you're saying, Elijah, which is obviously correct, that since Achilles is faster, he's eventually going to pass the tortoise. There's no question. What Zeno's forcing us to focus on is the part of the race before he catches the tortoise. So what he's really saying is he can't pass the tortoise because he can't catch the tortoise. And he can't catch the tortoise, that is, draw level with the tortoise, because no matter how closely he comes, as long as the tortoise has a head start, the tortoise is always going to be a little bit ahead of him, at the next instant. Although those leads will shrink infinitely, there's no moment at which he's ever going to completely close that gap. And so he can't pass him. And he can't pass him because he can't draw even with him. And so it's great. Elijah, you've now sort of cut the problem in half. Now we have to focus on there must be something wrong with this part of the argument that says he can't draw a level. Because we know he's eventually going to do that and pass him. But what's wrong with Zeno's argument? That's our challenge, right? Yes, yes, Elijah. It's a more frustrating problem. Zeno is a clever guy, right? Zeno found a way to frustrate us by taking a commonsensical situation and turning it into a real problem. What's wrong with this argument? Okay, well, that's a great point. So you've got us, into the part. Your whole way of questioning is drawn much closer to the solution by taking us to the portion of the problem that needs to be resolved in order for the whole paradox to go away. So why is it that Achilles can never quite draw level with the tortoise? Okay, so if anyone has another comment, go ahead. Otherwise, I'm going to just take it from there and build on what Elijah said, and actually, I think tell you what the resolution is. Okay, but I'm open to other comments or questions at this stage. So I think I've held you in suspense long enough, though. If any of you've looked ahead, you know the answer. But I'm willing to go with it now. Is that okay? Should we get on with it? Is he not assuming motion is an illusion? Well, he's saying in a bigger sense, Abraham. Yes, remember that all of his paradoxes are concocted to show us in some way the impossibility of motion, or the impossibility of motion as we ordinarily conceive of it. So that's true. But there's something else here that will resolve the paradox. We don't have to buy into that. Okay, so I think I'm going to just tell you. So here's the thing. What he's showing us, and this is a bit parallel to the first problem. I think it's quite parallel. Because remember, in the first problem, he's not really showing us that we can't leave the room. He's showing us that if we start counting up the points, in a finite interval, that the number of points is infinite. And what he's really showing us is we can never count up the points, in an infinite interval. But that doesn't mean we can't just take a step over the over the interval itself. So that's a bit problematic. That's even, to me, a deeper problem, is how can you actually take a finite step over an infinite number of points. That's not entirely clear to me, but we know we can leave the room, so we must be doing it somehow. In this problem, he's really not proving that Achilles can't catch the tortoise and pass him. He's showing us something else. And what he's really telling us, and I'll say it in plain English, he's saying there's no last instant at which Achilles fails to catch the tortoise. That's what this diagram is proving. I'll say it again. I'll put it in the chat room. There is no final instant. This he's showing, and he's actually proving it. And I agree with the proof. It seems absolutely irrefutable. There is no final instant at which Achilles fails to overtake the tortoise. But even so, there is a first instant at which Achilles will overtake the tortoise. Okay, that's partly paradoxical too. But there is definitely going to be a first instant at which some of you know and some of you were asserting. Of course, there's going to be some point in time at which Achilles is going to draw level with the tortoise. That's true. And then he will pull ahead. But what is not true, and this is what's bizarre, but it's the resolution, and again, the epistemological price we pay to resolve it, is that we have to acknowledge that there's no final instant at which Achilles fails to overtake the tortoise. There are an infinite number of instants at which he fails to overtake the tortoise, but that doesn't mean there isn't a first instant when he does, and that's the resolution. I'll bet you want me to say this again. I'll even type it in. Try and digest it, because it's a little counterintuitive, but once you have that, there's no more paradox. Let me just type it in. There is no final instant at which Achilles fails to overtake the tortoise. That's really what Zeno is showing us. There's no final instant at which Achilles fails to overtake the tortoise, but there is, of course, a first instant at which he succeeds. Which he succeeds. And that means draws level. There's no final instant which Achilles. There's an infinite number of instants, according to this diagram. If you keep extrapolating, it is an infinite sequence. It just never ends. He's going to get closer and closer and closer each time to overtaking the tortoise, but still failing to do so, right? And there's no final instant, regardless of their speeds or distances. There's no final instant at which he fails to overtake him. And that's what Zeno was arguing, and Zeno was using that as an excuse to further conclude that never overtake him. But that's fallacious. Although there is no final instant at which Achilles fails to overtake the tortoise, there is indeed a first instant at which he succeeds in overtaking the tortoise. That instant would be calculable precisely if we knew, simply we need to know their rates of speed, which we assume constant, and we need to know the head start the tortoise has, which is going to be some finite head start. And then we can easily calculate the first instant at which Achilles draws level, and after that always goes ahead. But notice, there's also no first instant at which he leads the tortoise. He will overtake him at some precise instant, that is draw level. But after that, there's no, it's the same argument in reverse. There is no first instant at which he will pull ahead. Although he will pull ahead, in an ever increasing distance. There's no first instant in which he pulls ahead either, which is just as bizarre. Zeno never thought about that or never needed to. And do you know why? And now if I tell you why, some of you may be struggling to digest this, which is, I'm claiming, the resolution of the paradox. Let's get in a much simpler way. And you can play this game with a child who has had arithmetic anyway. And then maybe you'll get it. Suppose I ask you the following question. What is the number Okay, here's a question. Nothing to do with Zeno's paradoxes. It's just to do with arithmetic. Okay? What is the number? And I'm not talking about whole numbers, I'm talking about real numbers, okay? What is the number closest to the number 1? What is the number closest to 1? Thoughts? 0.99, 0.9, 0.99. Some of you are saying 0.9. Okay, so but yeah, now Abraham's tacked on a few nines. So we're getting closer to 1 all the time, right? So 0.9 is close to 1. Ahmed says, but Tricia and Keith said 0.99. That's closer. Abraham has added, no, not equal to, closer but less than, okay? Closer but less than. What I mean by closest, I mean closer but not equal to, okay? So it's on the other side of 1. And you guys have all figured this out now. It's easy. You're just going to keep adding 9s, right? It's going to be 0 point, and then, in fact, an infinity of 9s, yes? And exactly, Timothy, it continues. It's infinite. So you realize that you can get arbitrarily close to 1 by adding more 9s in the decimal expansion. But you're never going to reach 1 that way, are you? So, okay, so that's the resolution of the paradox. I'll just put it in that different context. There is no last number before we reach 1. There's no final number before it's not a loop, it's an infinite series that gets closer and closer and closer but never reaches 1. So there is no final number that fails to reach 1. If you keep adding, if you go 0.99999 and keep adding 9s, it's an infinite number of 9s that you can add without ever getting to 1. In that case, there is no final number that fails to reach the number 1. But there is still a first number that reaches the number 1, namely number 1. Now, do you see the parallel? There's no final instant at which Achilles fails to overtake the tortoise. Like there's no final number that fails to reach the number 1, but there is nonetheless a first that succeeds in reaching the number 1, namely number 1. And similarly, there is no final instant at which Achilles fails to overtake the tortoise, but there's still a first instant at which he succeeds in overtaking the tortoise, which is when they draw level. Okay? Some of you are saying, yes, you get this? That's the resolution of the paradox. And some of you are going to have to think about this, okay? Those of you who still haven't figured it out, what you need to do is understand the meaning of a sentence in English, okay? The sentence that I typed in there, I'll read it again. There is no final instant at which Achilles fails to overtake the tortoise. There is no final instant at which Achilles fails to overtake the tortoise. That is equivalent to saying, for example, that there is no final number that fails to reach the number 1. If you take 0.9 and keep adding 9s, you're never going to get to the number 1. You can keep adding as many 9s as you like, and you get closer and closer and closer to 1, but you'll never get to 1. And so there's no final number. You won't reach the final number such that that's the number that's, the next number is 1. Why? Because you can stick another 9 in there. And similarly, analogously, you could keep dividing the space between Achilles and the tortoise. As Achilles gets closer and closer and closer to catching the tortoise, there's still an infinite number of points at which Achilles will fail to overtake the tortoise, even though there's a first point at which he will succeed. So Zeno very cleverly is focusing our attention on this infinite number of points at which Achilles fails to overtake the tortoise, and then concludes that he could never do it. But of course we know that just because there's an infinite number of points at which he fails to overtake the tortoise doesn't mean there isn't a first point at which he succeeds in overtaking the tortoise. And that, in plain English, is the resolution of the paradox. And those of you who got this, then it means the light has come on, and now you understand how clever he is in deceiving us with this argument, although we now understand what's wrong with the argument. Those who are still struggling with this, I can only suggest, like any problem in philosophy, this is not a mathematical problem, it's a conceptual problem. And what you really need to do is perhaps to write down the sentence that I've, copy and paste the sentence I typed in there, and meditate on that sentence until you really penetrate its meaning with respect to this problem. That's all I can suggest to you. Or maybe my explanation works for some people. And I've always found this in mathematics, that sometimes mathematics can be difficult, not because the math is difficult, because it's being explained in a way that may be difficult. So it depends on the style of the teacher. So sometimes you may need a concept explained a different way in order to get a handle on it, and that's a regular thing, a normal thing. So if my explanation doesn't quite work for you, and this is as clear as I'm capable of being on this, then you should go to Stanford Encyclopedia or go to Grunbaum book. There's a wonderful book by Adolf. I'll type his name. Grunbaum, Adolf Grunbaum, philosopher of Pittsburgh. I don't know if he's still alive. He wrote a wonderful little book, explaining all four of Zeno's paradoxes very clearly. Maybe his explanation would be better. But if you look online, you'll see lots of resolutions, and maybe one of them will be worded in a way that is, for you, more comprehensible. Is that fair enough? Okay, good. So I know some of you got this, and some of you maybe didn't get it yet, but you will. All right? I promise, if you think about it carefully and find an explanation that makes sense to you, you'll understand, because you know already in your common sense that Achilles will overtake the tortoise, and after that will never be behind. But at the risk of confusing you further, I just want to point out that the same argument works after he overtakes the tortoise. There's only one instant at which they're at the same spot, right? Wherever that is. Although there are an infinite number of instances at which he fails to overtake him, there's still going to be one instant at which he does, and they're going to be like level. But after that, there's no first instant at which he's ahead either. Because if I ask you the same question, so what's the first number after 1, right? So now we say, okay, they're level for a very, for one instant in time, and after that, Achilles will be ahead and will continue to be ahead until he crosses the finish line, for sure, and that lead will augment, just as the tortoise's lead decremented. Achilles' lead will increment after he's overtaken him. But nonetheless, I'll ask you the same question a different way. What is the first number? What is the first number bigger than 1? First number bigger than 1. Oh, well, they have to be. Erkin, wait a second. That's a different question. You're asking a totally different question. Okay? They can't be at the same spot because the tortoise is moving. He needs to stop for a second. No, that's not true. Let's say you're driving a car and you're overtaking somebody in a slower lane. Can you picture that? They're moving, the car is going at a steady speed, and you're overtaking somebody, right? If you had cameras on you, there'd be a moment at which both cars are exactly where the front bumper of both cars are exactly in the same spot. There's a moment where they're in exactly the same spot. Only one moment in time. It's not the case that one car has to stop for the other to overtake it. The fact is that as the faster car is passing the slower car, there's going to be one instant and only one instant in time in which their front bumpers are going to be exactly aligned. And after that, the faster car will always be ahead. Okay, so the tortoise doesn't have to stop for Achilles to overtake him. A slower runner is overtaken by a quicker runner without stopping. The fact of the matter is there's only one unique moment in that race when the two runners are exactly in the same place. And after that, the faster one's always going to be ahead. So that's another problem that you get bogged down in. But they're not stopping. They're always both moving at a constant rate of speed. So if I ask you what's the first number bigger than 1, and Keith Morris is saying, 1.00000, how many zeros? But then I keep saying no because you could stick in more zeros, right? You could always stick in more zeros. And so again, there's no first number bigger than 1, because no matter how small a number you name, and what you've just named is very small, very small difference between that and 1, we could still stick in more zeros, right? We can keep sticking in more zeros. So we never get to the first number bigger than 1, because there isn't. There's an infinite number of numbers bigger than 1. Right, good. You see, okay, and you see Erkin also. So on this view, Keith, it's the same as the previous part of the problem, where Achilles is catching the tortoise. No last instant at which he fails to overtake him. And similarly, and maybe just as counterintuitively, and Zeno didn't mention it as part 2 of this paradox, there's also no first instant at which he succeeds in overtaking him. And it's not a different paradox. I'm saying, just as there is no final instant at which Achilles fails to overtake the tortoise, there's also no first instant at which he succeeds in overtaking the tortoise. There's only one instant at which he draws level. And after that, he'll be ahead forever, until the race ends at least. But there's no first instant at which he's ahead, because there are an infinite number of first instants, if you like, after he pulls ahead of the tortoise. So it's the same problem through the looking glass, just in the other way around. Okay, and that part is what's counterintuitive. Okay, to me, that's obviously what the counterintuitive part. Of course, Achilles will draw level and pass the tortoise, but there's no last instant at which he fails to catch him, and there's also no first instant at which he falls ahead, because that number can always be subdivided infinitely too. Okay, so makes sense. All right, I'm glad, Mame, it makes sense to you. And so it's no longer a paradox. But we had to pay that little price, right? That twist, that epistemological twist of there being no final instant at which he fails to overtake the tortoise. Most of us had never thought of that in our common sense experience, right? So Zeno, by throwing this infinity into the mix, totally derailed our common sense temporarily, right? But we can reconcile that now with what we know to happen in the real world. That, of course, he'll overtake him. It's just that there's no last instant in which he fails to. Okay, are we good? All righty, good. I'm getting some yeses, okay? Again, don't worry. If some of you are still scratching your heads, that just shows you what a great paradox it is. And think about it more carefully, or look up a different explanation. Eventually, it will dawn on you what's going on here. Okay, I'm glad. So we're going to now tackle the third of the 3. And to me, at least, and we'll see what happens, to me, this third one is the most perplexing of all. Okay? It's going to play not only with space, but also with time, explicitly with time. And we're going to have to end up maybe doing something as bizarre with our notion of time as Zeno's compelling us to do with our notion of space. It's also going to be about divisibility, though. I mean, that's what's underlying this. It's a question of whether things are infinitely divisible. Okay, but it, at first blush, doesn't look like that kind of a problem. It just looks like another crazy, impossible thing that Zeno's going to argue for. But I think it's a lot trickier, in a way, to figure out what the resolution is. If you haven't looked at it yet, I'm sure you'll be scratching your heads in a moment. I love this problem. Don't do this at home, by the way, okay? This is the arrow paradox. And what Zeno's going to do in this paradox is he's going to claim that an arrow shot from a bow cannot possibly fly through the air. Okay? So you have an archer, a bow, draws the bow and shoots the arrow. And our common sense tells us pretty much don't stand, in the path of the arrow, right? If the arrow's flying through the air, and it's going to stick into something at the end of the day. But Zeno's saying, no, don't worry. The arrow can't possibly fly through the air. Okay? So here's the picture, or here's an illustration, which I'll share with you. But you can all visualize this problem anyway. It's a lot more straightforward to visualize. There's an archer with an arrow, and the bow is drawn, and Zeno, in this cartoon, he's tied him to a tree. So he's saying, "You still sure? Are you sure?" He's saying to Zeno or Zeno, "Are you sure? Are you sure that the arrow is not going to fly through the air?" So that's why I'm saying don't try this at home. But basically, the argument that Zeno is making, whether he's tied to the tree or not, he's saying when the archer lets go of this bow, it's impossible for the arrow to fly through the air. Okay? So some of you may now be saying that's completely crazy. So how could he possibly argue for a conclusion that crazy, right? What kind of argument could possibly be concocted for us to conclude that an arrow released from a bow can't fly through the air, right? Sounds on the face of it, absolutely, Abraham. It's counterintuitive to say the least. Okay, so yeah, it's great. And you're wondering how could he? Okay, well here's his argument. Again, you got to clear your mind. Okay, not possible, absolutely not possible that an arrow can't fly through the air if it's. But here's Zeno's argument, and it's really clever. I think it's really clever, and it's going to make you all think twice. Regardless of that there's something wrong with it by now. We know there's something wrong with all his arguments. He knew too. But here's the challenge is why. Well, let me give you the argument first, Keith. It's not so much about straight lines. I mean, that's a different thing. We're assuming an ideal projectile moving, in an ideal space. Okay. The argument won't have to do with, straight lines so much. Here's the argument. So Zeno says, and this is what we call a reductio ad absurdum. It's an argument that depends. It's an indirect proof. It's assuming the thing we want to disprove, and then showing that it's a contradiction. Okay? So Zeno says, imagine that the arrow is flying through the air. All right? Zeno's saying, okay, well, suppose you imagine what you think, is what happens in normal life, that the arrow is shot from a bow and the arrow is flying through the air. So Zeno says, suppose the arrow is flying in the air. So imagine now that the arrow is in a certain place at a certain time. As it's flying through the air, it must be occupying a certain place at a certain time as it moves, correct? So imagine, Zeno didn't have high-speed cameras, but we do. Imagine we had a high-speed camera on this arrow, so we could see it, right? You could see a high-speed camera on bullet now. Arrows are much slower, so we could put a high-speed camera on the arrow's trajectory, and at some point, we'd be able to freeze the frame, and we'd all see the arrow in flight, but it would be like a frame, so it would be at a certain place at a certain time. Are you with me so far? Okay, Timothy says yes. So as the arrow is flying through the air, Mama, yes, Abraham, yeah. Also common sense, right? The arrow's at a certain place at a certain time. Okay, as it's going to. So here's Zeno's argument. If you assume that, says Zeno, now you're done. Now he's going to tell you can't move. Why? Because he says the following. If the arrow is here now, right? He's saying, okay, just what we've all agreed to. Not all of you, but I see a bunch of yeses. You've agreed that the arrow, as it's flying through the air, must be at some place at some time, some given place at some given time. And so we would say, okay, the arrow is here now. So here's Zeno's argument. This is diabolically clever, I think, although very simple to say. Zeno says, okay, suppose the arrow's here now. Well, he says, if it's here now, then it obviously can't just be arriving, right, in its flight, or it wouldn't be here now. Nor can it be departing, or it wouldn't be here now. So if the arrow's here now, but it can neither be arriving here now because it's already here, nor can it be departing here now because it's already here. So how does it ever move? Because if it's ever moving, then it can never be here now. That's right, Erica. A stunned silence. Some of you immediately got this. This is a diabolically clever, right? You're lost. Okay, I'll repeat it. It's a little bit like the tortoise, in Achilles, but it's more, where's your coffee? That's right, Timothy. You got to get the neurons firing for this one, okay? I'll say it. That's why it's still, Mimi. That's exactly right. He's saying, and you're all agreeing initially, because, of course, that's the trap, right? But think about the alternative is words in a way. But he's saying, look, I'll be straightforward with you. If we imagine this arrow in flight, then at every moment of time, it must be somewhere, right? It hasn't vanished. It's not like it was shot there and disappeared and reappeared. It must be traveling. So it's at every moment in time, it's some place, right? Correct? At every moment in time, the arrow must be somewhere. Well, clearly, sure, it exists. So it must be somewhere. At every time, at every moment of time, the arrow is somewhere. But then Zeno uses that fact, apparent fact, to make its impossibility of flying, because he's saying, okay, if the arrow's here now, I'll just repeat the argument. If the arrow's here now, says Zeno, it can't just be arriving here, or it wouldn't be here now. Agreed? I mean, we're not saying it's almost here. We're not saying it's on the way here. We're saying it's here. At this point in time, it's here, so it can't just be arriving. Okay? And by the same token, if it's here now, it cannot be just departing either. It hasn't just left, because it's still here, right? So it can neither be arriving nor can it be departing, because it's here. But if it can neither be arriving nor departing, then how can it move? So you get it right. You see, good. Right. Wow. Yeah. Wow, indeed. I mean, it's really clever, right? He's using our own assumption about the arrow being here now. It's, to say, well, wait a second. If it's here now, it can't be just arriving. It can't be just departing, or it wouldn't be here. And so, how can it move? No, of course you didn't think about it like that, because you hadn't read Zeno or Zeno. Yeah, it is interesting. I agree. It's yeah, it changes everything. It does. It does. It's really pretty. It's a pretty unique insight into this problem. So let me ask you a different question. This is easy to get. This is I mean, easy to get his argument. You realize, but then we also know that there must be something dreadfully wrong with his argument, because you're still not going to stand in front of the moving arrow, right? Like if someone's, that bow is aimed at you, it's not like you're going to say, well, the arrow can't move. So there must be something wrong with his argument. So I'll repeat the argument once more, and I want you guys to really get the neurons firing and try to tell me, now, wait a second, what might be wrong with the argument? Because we also know, by the same token, the arrow is flying through the air. So Zeno was saying, but if the arrow is flying through the air, it has to be here and now there has to be, a given point where it's here, a given point along the way, always going to be an infinite number of points. In fact, when it's at this time here and now, it's here and now at some point in its flight, then it can't just be arriving, or it wouldn't be here now, here and now, and it can't be just leaving, or it wouldn't be here and now. And therefore, if it's here and now and it can't be arriving and it can't be departing, then it can't move. Because if it were just arriving, it wouldn't be here. And if it were just departing, it wouldn't be here. And that's true of every arbitrary point in its trajectory that we call here and now. So how can it ever move? And what's our choice? What do we have to deny in order to deny Zeno's argument? This is where it gets even more diabolical. I mean, we could say that, therefore, what really Zeno is telling us, I'll give you two solutions now, okay? I'm going to give you the very standard solution, and I'll give you I think it's the more philosophically interesting solution. And we'll start with the standard solution. And I'm going to put up the whiteboard for this one, because I have to write a simple equation, okay? We know that the distance that an object travels in space is equal to the velocity times the time, right? Should I use capital letters to make, because I don't have so distance that something travels, assuming a constant speed, right? Is equal to its velocity, will soon to be constant, times the time. Have you all seen that equation? There's nothing on the whiteboard yet. Oh, well, I'm seeing the whiteboard. Maybe I'm somehow not sharing it. Just a second. Maybe press enter. Oh, you see it now. Hang on. Oh, now you see it. Okay, so there's some kind of weird time delay. Okay, so there's some other paradox because I'm typing it, but you're not seeing it. Okay, some other weird thing. Okay, now you see it? I should press enter. Well, I did. Okay. So you all know this formula, correct? Yeah, D equals VT. Exactly, Mimi. Distance is velocity times time, correct? Now, good. Okay. I mean, that's high school, right? High school physics. So if we're assuming a constant velocity, and then we can precisely calculate how far something's gone, but by it, how fast is it moving and how long did it travel, and we get the distance from that formula. That's not problematic, and that's not paradoxical. So one way of objecting to Zeno's argument is by looking at this formula and saying, wait a second, when the arrow is here now, assuming what Zeno wants us to assume, that the arrow is here now, right? How much time are we giving the arrow in which to travel? If we're saying the arrow is here now, then how much time are we actually giving the arrow? Right? When the arrow is here now, right? That time here now, how much time is that? When the arrow's here now, how much time is that? Exactly. Great. None at all. Exactly. The time at any given instant is 0, right? At any given instant, if we're saying the arrow's here now, well, it's not at rest, Timothy. Please understand something. This is really vital. The arrow has velocity. The arrow's not at rest. But what we're doing is we're not giving the arrow time to move. All right? Well, by saying that the arrow's here now, right, it's very important. It's a subtlety, right? But it's a key one. We're not saying that the velocity is 0. But we're saying if we don't give the arrow any time in which to move with that velocity, then what's the distance that it travels? I mean, if the arrow is here now, then we're giving it no time, right? Then if the arrow's here now and we've given it no time, then obviously, exactly right. Then we're saying, well, obviously the distance is also 0, right? Because we haven't given it time. So if you don't give a thing time to move, then of course it can't move. So therefore, Zeno is just pulling a fast one on us. But Zeno is like tricking us, because notice something in this equation, that if we make one of these two things 0, if we make either the velocity 0 or the time 0, then the distance is 0, right? If the arrow has no time to travel, then of course it didn't go anywhere. And so that is one way to refute that paradox, by saying Zeno, by claiming that the arrow is here now, that's fine, but because it's neither arriving nor departing, you are giving it 0 time in which to move. So it's not very surprising that if we then calculate how far it moved, that since one of these variables is 0, the distance is 0. But notice something, just because that may be the case, that does not mean that the velocity is 0. Velocity could be huge, right? If we make the time 0, then of course it didn't go anywhere. That doesn't mean it has no velocity, correct? Could have a really huge velocity. We just need to give it time to travel someplace at that velocity. Are you with me? Good. Okay. So that's how you answer Zeno. You say, now, Zeno, if you gave it a little time, of course it would be moving because it has a velocity. So just because t equals 0, and you're telling us, therefore, d is 0, it's not going anywhere because we're not giving it time to go anywhere, that doesn't mean it's not moving. Could be moving very quickly. We're just not giving it any time in which to move. Okay? And that's pretty simple, right? That's not as difficult to grasp, actually, as the Achilles and tortoise solution, is it? It's much more straightforward. I mean, if you don't give the thing any time to move, not surprisingly, it didn't go anywhere, right? But as soon as you give it a little time to move, then certainly it's going to go somewhere. Yeah? And the more time you give it to move, assuming a constant velocity, obviously, the more it's going to travel. Okay? So, of course, the arrow flies through the air, but you have to give it some time. And by saying it's here now, you're not giving it time. Okay? So I think a lot of people are saying yes. That's actually, I think, pretty simple to grasp. I think that's one way in which you can very clearly refute Zeno, but there's another way. And I want to share that with you now because it's more counterintuitive. And I think that it would make Zeno laugh more or make Zeno chuckle more or smile more if we discuss that. And here's the other way we can attack his argument. So think about this. He's saying to us that if we consider the arrow to be here now, right, which we're still saying, it could be here now on its way, right? It's here now. And he's saying it's neither arriving or it wouldn't be here now. And so it's also not departing because it wouldn't be here now, right? I mean, not much is the same argument. And we can refute it in a different way, but it's more shocking because what we have to give up to do that, and we may have to give it up anyway. He's really saying to us that if the arrow is not just arriving and not just departing, then it's not so much that it can't move. If it's here now, what he really is saying to me is that if it's here now, and it's not just arriving and it's not just departing, then it's kind of stuck in this now, and it can't get to the next now. There's no way for it to get to the next now. That's why it can't move, because it can't get to the next now. Are you with me? Anybody with me? If it's kind of stuck at this now and it can't get to the next now. Right. But wait a second. Then we get the real issue. If, we get the real issue. That is, there is no next now. Because there is no next now for the same reason that the number of nows in a given interval of time is infinite. We're not thinking about space, now we're thinking about time. So how many, for example, how many nows are there in a second? No, just 1 second. I'm not asking you how many seconds there are in a second. How many seconds are there in a second is most likely 1 second. I think we'd all agree. Okay, not more and not less. But I'm asking you how many instants of time are there in a second? Can't we divide that into a half and say there's 2 half seconds, Erica? If you have a stopwatch, any of you have done sports, you know, a stopwatch measures normally what? Hundredths, right? Yes, Elijah, we're back to this. Now we're back to the same problem of infinity, exactly. There's an infinite number of instants in a second, exactly, Abraham. So any interval of time, or however finite, can be divided into an infinite number of instants. So it now becomes more analogous to the first two paradoxes, right? Because Zeno was saying, wait a second, the arrow can't get to the next now because there is no next now. Between each two instants of time, there's always an infinite number of instants. An infinite number of instants. Yeah? Are we clear? So of course it can't get to the next now, because there is no next now. Between each instant of time, between every two instants of time that you arbitrarily nominate, there's going to be an infinite number more instants that we could pick out in there. And so the arrow can't get to the next now. There's no next now to which the arrow can get. Just like there's no final moment before Achilles overtakes the tortoise. There's no next now that the arrow can get to. But that still doesn't mean then we can use the same refutation of the Achilles and tortoise problem and say, yeah, but just because the arrow has to traverse an infinite number of nows in order to traverse space, it does not mean that it can't traverse a finite interval of space in a finite time, even though it's traversing an infinite number of nows. Just like you have to traverse an infinite number of points in order to get to the door, you can still get to the door. So a finite chunk of time could contain an infinite number of nows, right? Just as a finite interval of space could contain an infinite number of points. Okay? So that's a second refutation, a second way of tackling the problem. All right, depending how you want to look at it. I think the first way is actually simpler, using the distance equals velocity times time argument. But also more subtly, we could go to this problem of there being no next now, but that doesn't disprove motion. Just because the arrow can't get to the next now doesn't mean the arrow can't fly through space in a finite interval of time. Okay? It's analogous to the previous paradoxes that we've already resolved. Is that fair enough? Great. Yes, that's right, Timothy. That's exactly right, Timothy. Zeno is suggesting that motion is an illusion. So I have time to throw one more curveball at you. Now that we think we're out of the woods with Zeno, turns out he might have been right. And I'm going to throw one more curveball at you, okay? We're going to fast forward to our time. And we watch videos, right? We watch movies. Yes, ma'am. Sorry, this one's been up my sleeve the whole class, okay? I'm going to leave you with this. And here it is. Okay, any of you ever make films or make movies or play with movie making software? Sure, okay, good. I do too. And it doesn't matter about the medium. We could be talking about 8mm film or, or digital studio. It doesn't matter. What we call a video is a sequence of still images, isn't it? Absolutely. And the human eye itself cannot detect more than how many frames per second? Actually, it's 25, Erkin. Good guess, but it's fewer than that. I think 24 is the number. And once we start showing more than 24 frames a second, the eye suddenly perceives things as continuous, whereas we actually know that they're a bunch of discrete. We're looking at a sequence of discrete frames, right? It's like a cartoon flip book. Have you ever seen those kids' books? Like the hard copy? It's a flip book, right? And you know what's in the flip book. Is anything moving in the flip book? No. Nothing's moving in the flip book, right? The flip book is actually exactly right, Timothy. It is a sequence of still photos. And what we produce by flipping through it at a high speed is this beautiful and charming animation, right? And cartoons are the same. You know this. What we call an animated cartoon is very many. It's a sequence of very, very many still photos, right? So what's moving in a cartoon then? Or what's moving in a flip book? Or what's moving in a video? In fact, nothing is moving. Yeah, the pages, but the images. It is not the case that the video or the flip book or the cartoon contains a character who's moving. That is an illusion, complete illusion. And where is it being produced? In our minds. So it's our minds that are moving. The illusion of motion is produced in our minds. And that, if you want to support Zeno, and if we bring Zeno back, today and show him, you know what, Zeno, you were right. Look, here's an animation studio, and look what we're doing. We're creating an illusion of all kinds of things moving around. Actually, it's just a bunch of sequence of still images, and it's the mind that stitches them together into a continuous motion. But it's not really happening. So then, what's the punchline of this? The punchline of this is, if Zeno's right, and if reality is a cinema, or if reality is an animation, then we have one more question, right? What's the frame rate? What is the frame rate of reality, right? How many frames per second is reality? And there's actually a physics computation that will tell us that reality also, the universe itself, may have a frame rate. The universe itself may well be a sequence of still images, okay? And that it actually is also connected by a frame rate that makes us look at it as continuous. It's much, much quicker than 25. It's more like a septillion frames per second. But it's a very high frame rate, and that's why we can't tell. However, I would still not stand in front of the moving arrow. Okay, I mean, we can conceptually maybe support Zeno with that kind of argument, but I still wouldn't stand in front of the arrow. Okay, so in a way, maybe the paradox is still with us, because if the universe has a frame rate, and it's really just a sequence of still images being run together at extremely high speed, then really nothing's moving through the universe either. Except you still don't want to stand in front of the arrow, okay? So we've resolved Zeno's paradoxes, but we still have some interesting questions at the bottom of it, right? Even so, we could still look at that as a lens through which to raise ontological problems and also to raise problems about infinity. So I hope this has been fun for you to look at this ancient guy. And we're going to fast forward next week. So I'm going to tell you, just for your own reading, if you want to read ahead, next week we're going to look at something called Anselm's That's the next. We're going to fast forward more than 1,000 years to Anselm's ontological argument, a very famous argument. And this argument is also somewhat paradoxical. And Anselm is going to prove to us by logic the existence of God. Okay? And that's even more shocking than Zeno. Because most of us, whether you're religious or not religious, most of us will generally view belief in God as faith. We have faith, and that's why we believe, not because anybody proved it. And in fact, we would say from a logical or scientific point of view, traditionally, you cannot prove or disprove God's existence. The existence of God is not something which is subject to our own kinds of proofs that we can concoct, be they laboratory experiments or be they logical experiments. There's no proof or disproof. There's only faith. But Anselm, in around 1,000 in the 11th century, came up with this ontological argument in which he actually purports to demonstrate conclusively that God must exist, and that's very paradoxical, whether you believe in God or not. And we'll look at the argument on Monday in a plenary, and then we're going to look at some objections to it by people who actually believe. There were a lot of philosophers who believed in God, but they said there's got to be something wrong with this argument, because how can we prove this? So that's going to be our challenge next week. It's very famous argument, and it's still being debated, and it's in your textbooks. Okay, so look ahead if you wish. Have a great weekend, everybody. I'll look forward to seeing you in the plenary on Monday. So think about Zeno, okay? I hope your minds are a little blown by Zeno. And then get ready, because we got more coming up. We're going to prove next week that God exists, okay? So take care, everybody. You're more than welcome. Take care. Thanks for your interactions today. I'm glad to see you engaged with these problems. Have a wonderful weekend, and we'll see you all on Monday. Okay, bye for now.